Hi, good morning. This is the 200 DF class of Tuesday, June 2nd. I started without recording, so now I'm restarting, okay? So we were working about the ideal gas law. PV is equal to nRT, where P is the pressure, V is the volume, N is the number of moles, R is a constant of value 831, and T is the temperature, but be careful, this temperature should be expressed in kelvins, okay, not in centigrade degrees. Exercise 1 we did last time. We saw that it was important to have kelvins. Exercise 2, your tire contained an air at pressure 2.6 bars at 20 degrees. After driving on the highway, the tires reached a temperature of 50 degrees. What is then the pressure inside the tires? Well, the idea here is to take the ideal gas law and to realize that this can be written as PV over T is equal to a constant. We don't need N and R in this situation because we don't know how much air we have inside. It doesn't matter. So we say PV over T is a constant. Okay, if PV over T is a constant, then PV over T before the transformation is equal to PV over T after. So we run P1 with V1, T1, the conditions before, P2, V2, T2, the conditions after. And we replace all that, which gives us P2 is equal to T2 P1 over T1. We put in the values. For T2, we have the values in Kelvin. So it's 273 plus the value in centigrade, 323, and T1 is 273 plus 20, 293, times 2.6 bar, the initial pressure, and I get 2.87 bars. Okay, so the pressure inside the tires is increasing a bit while you drive. Okay, now we have exercise 3. Are you done with exercise 3? I'm back with you now. I'm no longer recording what we did before. Did you do exercise 3? I don't know. Open your mics, please. Somebody. Yeah, okay. There's life on the other side of the line. Okay, so you have a tire which has been inflated at 27 degrees Celsius. So this is temperature 1. This is 27 Celsius. So immediately write it as 300 Kelvins. Is that correct? 73, 89. Okay, 300. This is the inflation temperature. The pressure P1 is 2 bar. We will see what unit we use later. After the car has driven, tire pressure becomes 2.2 bar. So pressure 2 is equal to 2.2 bar. And assuming constant tire volume and approximated tire air by a perfect gas, calculate the temperature inside the tire. So it's very similar to the exercise we did before. It's not much more complicated. Okay, you take P1 V1 over T1 is equal to P2 V2 over T2. You assume constant volume, so it's again the same thing. You can remove the volumes from the equations because the initial volume is equal to the final volume. And now, so you have T2, which is equal to what? T2 times P1, so it's going to be divided by P1, is equal to P2 T1. P2 T1, okay? And what do we see? P2 is 2.2, P1 is 2, and T1 was 300. So that gives us how much? That gives us, let me compute that. That gives us a 10% increase. Yeah, of course it's 10% because this is 2.2 over 2, this is 1.1 over 1. 1.1 is times 10% plus 10%. So this is 330 Kelvin. And now if you want to know this temperature in centigrade, you have to remove 273, so it gives you 57 centigrade. Okay? D'accord? Now I will give you another exercise, which is of a different type, because these two are a bit boring, I realize. Okay? But this is not in the class, so I would like you to write it down. Exercise 3, determine the volume occupied by 2.34 gram of CO2 gas at STP. This at STP means at standard temperature and pressure. Okay? In French, we say conditions normales. Here, they say standard STP, standard temperature and pressure. The volume occupied by 2.34 grams of CO2 gas. So you have to compute the number of moles, of course. And then you have to use the law PV is equal to nRT, but this time you are not going to compare two situations, you are going to use the law in itself. Okay? You are at standard temperature and pressure, so you know the pressure, it's 1 atmosphere. The volume, this is what you have to compute. N is the number of moles, so you have to determine the molar mass of CO2 and decide how many moles we have. R is a constant, it's worth, now wait, because I have to see in which units that is. So here you have to use the value R is equal to 0.0821 liters times atm divided by mole times Kelvin. So be careful, this R, it can have different values according to which units we are using. Okay, for instance, this exercise, I took it from a chemistry book, and in chemistry books, they do things a bit differently. 0.08206, 206. Okay, this is the R constant. It's not complicated, you just need to compute all these things. Can you try to do it? Are you trying? Are you doing the exercise? Hello, I hear nothing. Ah, yeah, leave it open. This mic. Tell me when you are done. Can I start? Please open the mics before I become completely crazy. Yes, thank you. Okay, so we said we use this formula, and how do we use it? We need to determine the volume. Okay, so the volume is clearly nRT divided by P, right? And so we need to compute all these quantities. Okay, so first of all, what is N? N is the number of moles. Okay, and you remember we did that in the beginning of the year. We can determine the number of mole by writing the mass divided by the mass of a mole. It's the same, okay? If you have a mass which is equal to the mass of the mole, this will give you 1. You have 1 mole. If the mass is twice the mass of the mole, you have 2 moles. And if the mass is 10% of the mass of a mole, you have 0.1 mole, okay? So the number of moles is given by 2.34 grams. I will put the unit, 2.34 grams of CO2. And the molar weight is what? So for that, you need the CRM table. Okay, and to look up the weight of a mole, you need to see the weight of carbon. Carbon is 12. And then you have O2. So O is 16. So in principle, it's like that. Okay, 16 plus 16, you have CO2. You have per mole 1 carbon and 2 oxygens. Okay, so 16 and 16 is 32, 42, 44. Okay, so this is 2.34 above 44 grams. You understand how this works? The mole is the quantity of molecule corresponding to Avogadro number. And this is the weight of such a quantity is given by the molecular weight in units of atomic mass expressed in grams. Okay, so this will give us the number of moles. And the number of moles is therefore 2.34 divided by 44, which is 0.0532. Sorry, I didn't have space. Okay, the number of moles is 0.0532. Right. And now we can compute our volume. The volume is the number of moles. So 0.0532 times what? Times R, which has this value. So you need to look at the values of R. You see, I took these exercises in different books, and they are done with different units, and I decided to leave it like that because sometimes you are trying to determine the volume in liters, And here this is what they did. They use a value of the R constant, which is in liters times atmospheres divided by moles times Kelvin. Okay, the value I gave you, the 8.31, this was the value in another unit, which was joules per Kelvin per mole. Okay, so it's just a different unit, and of course a different unit constant take different values. So look at the constant that is given, look at the units that are given, and this tells you that the volumes are in liters and that the pressures are in atmospheres. This is what it tells you. Okay, so now we are at standard temperature and pressure. Okay, so this will tell us, of course, we need to put here the value of this constant. I'm sorry, this is what I wanted to say just before. We need that. And now we put the temperature. We are at standard temperature and pressure. So we will take 20 degrees Celsius, but we should write that in Kelvin. So it's 200. Oh yeah. So this is 293 kelvins. I should do that more often. It makes you speak. So I hear life on the other side, and it fills me with hope. So times the temperature divided now by the pressure, which we will put at 1 because the pressure is in atmospheres, and so the standard pressure is 1 atmosphere. Okay. And so, how much is that going to give us? This is 0.0532 times 0.08206 times 293. This gives us 1.28 approximately liters. Okay. Why 1.28 liters? Because, as I said, the constant R is given in liters times atoms. So this is the only reason why I said the result is in liter, because I see that this constant is in liters. So if you have here all the other values in the right constant, then you will get here a volume in liters. Okay, that's all. Okay. Okay. So I will give you a last exercise and then that will be it. The last exercise, just to illustrate a bit this law. Okay. So, well, let me write it. This is going to be exercise 4. Okay. And it says the following: ideal gases in a closed container have volume V and temperature T. So these are the initial conditions. Okay, we have an ideal gas in a container with some volume V and some temperature T. Okay, the final temperature is, so let's call it T prime. The final temperature is 5/4 of the initial temperature, and the pressure is 2P. Okay, What is the final volume of the gas? What is the final volume of the gas? Okay. Well, think a bit about it. Maybe we can do it together as you like. So this is again one of these exercises where you compare one initial and one final situation, but here you have all the three variables, PV and T, which are changing. Okay, so in order to do this, you say P1 V1 over T1 is equal to P2 V2 over T2, because the ideal gas law tells you that PV over T is equal to some constant. Okay, so you don't worry which constant it is. Yeah, it is NR, but we don't care about that. We don't need that. We just compare the initial constant, the final constant. Okay, and what we are looking for is an expression of the final volume of the gas. So what we want is this, right? But now we have info about P2 and T2, okay? We know that the final temperature, which I call T prime here to create confusion in your young minds, this T prime, this is T2, and this is 5/4 of T. And the P2, the pressure, becomes 2P. So this is 2 times P1, and sorry, this is 5/4 of T1, right? So now I can write that this is 2P1 V2 divided by 5/4 of T1. Aha. Let me rewrite this side of the equation. P1 V1 over T1. Okay? So what do we do with that? What would you do when you are faced with an equation like this? What do you do instinctively? To talk to me. Tell me. Don't be shy. Hello. What do you do? Before you go any further, you simplify this equation, right? You see that you have T1 on the two sides. It's the same variable. You can simplify. You see that you have P1 on the two sides. You simplify. Okay? And you are left with what? You are left with V1 is equal to 2V2 divided by 5/4 divided by 5T1, and the over 4 goes above. Okay? 1 over 5/4 is 4/5. Okay? So the 4 comes up. Okay? And so finally, we have 4 times 2, 8 divided by 5. Sorry. I wrote the T1 here. I shouldn't have. Emergency, where is my eraser? It probably ended up in the kitchen. Okay, so don't worry, this is not here. Okay, so we have 2 times 4, 8 over 5 times V2, but we are looking for V2. Okay, we are looking for V2, so we can write that V2 is equal to 5/8 times V1. I have inverted this equation, and so the volume becomes, if you want to answer this problem, okay, you can say the volume V becomes 5/8 of V. Oops, sorry. And that's the answer to the problem. I'm sorry, you didn't see the page for some time. You see, you have P1 V1 over T1 is equal to whatever you replaced with. Then P1 cancels, T1 cancels, and you are left with V1 is equal to 4 times 2 V2 over 5, which you can write as 1/5 of V2. So V2 is 5/8 of V1, and that's it. Okay, this is what you determine from the equation, from this approach, but this tells you that the volume is becoming 5/8 of the initial volume. Since the initial volume was called V in the exercise, you can say, okay, the final volume is 5/8 V, so the volume has decreased. Okay, does that make sense? Does that make sense that the volume has decreased? Always ask yourself the question. The final temperature is a bit higher, okay, but the final pressure is the double. Is it normal that the volume has decreased? Yes, if you have increased the pressure inside something, of course the volume has decreased. Okay, this is consistent. Always kind of check it. Okay, I thought I would stop here because I finished the course and I don't see why I should keep you online for 1 more hour just to fill in the time. Do you have questions about what we did and about these last chapters? No, ça va? Do you have the impression you got something from this online course during confinement? How do you feel about that? Yeah? Okay. Okay, thank you. That's I hope everybody's the same opinion. I hope everybody's the same opinion as you, but yeah, I'm happy if this brought you something. And we will see next year how people are doing. Okay? Now it seems that this epidemic is going to leave us because it's not picking up. Let's hope. And voila. Okay. So I'm going to terminate the class now. It was very nice to teach to you guys. Quiet, serious. It was a nice class and I had a lot of pleasure. And I hope to find some of you next year. And otherwise, we will meet in the corridors. Okay? Bye. Bye bye, everybody. Bye bye. Have a good summer. Bye. Bye.